بسم الله الرحمن الرحيم. أحبتي طلبة الصف الرابع، سنقوم بحل المسائل الخاصة بموضوع معامل يونغ. We are going to solve the problems associated with Young's modulus. We have here problem number 2. What is the amount of length that occurs on 2 meter long steel wire with diameter of 1 millimeter if a mass of 8 kilogram is attached to its end? G is 10 meter per squared second. The solution start with finding the radius. We don't need the diameter. The diameter is 1 millimeter. We need the radius. So if the diameter is 1 millimeter, the radius is 1/2 or 0.5 millimeter, which is equal to 0.5 times 10 to the minus 3 meter. We have to change it from millimeter to meter. Now from this value of the radius, we calculate the area, cross-sectional area of the wire, which is a circular shape. Its area is pi r square, which is equal to 3.14 times 0.5 times 10 to the minus 3. The radius is square, so this value is squared. This is equal to 0.78 times 10 to the minus 6 squared meter. We also need the force F. The force F is equal to the weight of the mass attached to the wire, and it's equal to mg according to second law of Newton. F equal mg. M is 8 kilogram, G is 10. Now we can apply the Young's equation, which is y equal F L naught over A delta L. Young's modulus is 200 times 10 to the 9. F is 80. F is 80 Newton. L naught is 2 meter. A, we calculated it. It's 0.78 times 10 to the minus 6 meter square, and delta L is the unknown. This calculation is simple. You can do it. Then delta L is equal to 0.001 meter. This is the second problem. The third problem, a wire with a cross-sectional area of 0.5 millimeter and length of 120 centimeter hanging vertically. What is the perpendicular force that needs to be applied to its end that its length become 121.2 centimeter? Young's modulus for the material is this. The solution is, we have to find delta L. We have the new length and the original length. So the delta L, the stretch in the length, the elongation, is 121.2 minus 120. It's equal to 1.2 centimeter, and we have to change it to meter. So it's 1.2 times 10 to the minus 2 meter. And also we need the area, the cross-sectional area, pi r square equal 0.14 times 0.5 times 10 to the minus 3. All of that is squared, which is equal to 0.78 times 10 to the minus 6 meter square. The same cross section of the last problem. Now we can apply Young's equation. Young's modulus is equal to force times original length over the cross-sectional area multiplied by the elongation delta L. To find the force F, Y is equal 1.4 times 10 to the 10th equal to F times L naught, which is 120 times 10 to the minus 2. We multiplied it by 10 to the minus 2 to convert it from centimeter to meter. This is divided by A, the cross-sectional area, 1.2 times 10 to the minus 2 times 0.78 times 10 to the minus 6. This is the cross-sectional area and this is the delta L. Also, the calculations are simple and you can do it in your notebook. So F is equal 109.9 Newton. It's 109.9 Newton. The other problem that we are going to solve is problem number 6. A bronze wire with length of 2.5 and a cross-sectional area of 1 times 10 to the minus 3 squared centimeter, pulled and elongated 1 millimeter. All these numbers must be converted. This must be converted to meter and the area must be converted to meter squared. By attaching an object of 0.4 kilogram, calculate Young's modulus of the metal. Consider the gravitational acceleration is 10 Newton per kilogram. To answer this problem, we have to find the area and the force in meter square and in Newton. The area is 1.1 times 10 to the minus 3 times 10 to the minus 4. This number will convert the centimeter squared to squared meter. F is equal the weight, which is equal to mass times the gravitational acceleration g. So it's equal to 0.4 times 10. This gives 4 Newton. The elongation delta L is 1 millimeter, which is equal to 1 times 10 to the minus 3 meter. Now we apply this equation. Y Young's modulus is equal to force times original length over the elongation delta L times the cross-sectional area A. So F is 4 times 2.5 over delta L, which is 10 to the minus 3 times 10 to the minus 7, which is equal to 10 times 10 to the 10th, which is equal to 10 to the 11 Newton per meter square. Now we are going to study this section, elastic and plastic deformation. There are two types of deformation. The first one is elastic deformation, and the second is plastic deformation. So the question is, what is the difference between elastic and plastic deformation? Elastic deformation is a temporary deformation. Temporary deformation. We can plot this graph between the stress and strain to show the elastic and plastic deformation. The elastic deformation lies at this region. Elastic deformation. It is in the limit of elasticity. It is temporary. It is temporary, and we can apply Hooke's law at this region. Plastic deformation is at this region, and it is permanent, and we cannot apply Hooke's law at this region because the plastic is the deformation is permanent. So elastic deformation, the temporary increase in length or shape of the object within the elasticity limit with respect to Hooke's law. Thus, when the effective force is gone, the object returns to its original situation. And the plastic deformation, the permanent increase in length or shape of the object out of elasticity limit without applying Hooke's law. Thus, when the effective force is gone, the object doesn't return to its original situation. This is the difference between the two types of deformation. Memorize this graph. Thank you. Have a good day and goodbye.